Hello, everyone. Good afternoon. Hope y'all are enjoying learning about solid waste and landfills. I think landfills are really cool. And so I'm going to be teaching y'all today about how to read contours and how to calculate slopes for landfills. So where this comes into play is for the various site maps and drawings that a site might have. This can be used to look at the bottom layers of a landfill, the top cover, final elevations, various things. So I'll be running through that today. There we go. So what are contour lines? They connect points of the same elevation and they should never cross. If your contour lines cross, then there's something wrong. So if you see on the left here, whenever your contour lines are closer together, that represents a steeper slope. And then on the right, if they are further apart, more spread out, they are a more gradual, shallower slope. There we go. Yes. So different different features that can be described with a contour line are, so on the left here, you'll see a hill as the circles get smaller and smaller, you'll see the number increases. That means the land is raising as you go inward. So that means it is going up. And then if you look to the right on the depression, as the circles get smaller and smaller, the number decreases. So that means you're going down in elevation. So that's kind of like a pit, a hole, something of that nature. Keeping so those are for circular features, and then keeping for that for more angular features. On the left, you see a ridge as you continue from left to right, or I guess if you want to look at it from right to left, as you go from right to left, the contours increase slowly. Um, so that means the slope is going up, but here in the middle of the ridge, the contours are more closer together than on the ends. So that means it is more of a steeper slope right there. And then looking to the right for the ravines, we see they increase from right to left as well, but the way the shape is, it's a little bit more gradual. It's not as bunched up together as the ridges. Um, so that is that. So what is a contour interval? It is the difference in elevation between the two contour lines. So for instance, we have down here, we have a contour interval of 2 feet. So how you can describe that is from start to end, you have 1, 2, 3, 4 lines, and each line represents a 2 foot difference. So then you do the 4 lines times the 2 feet per line to get 8 feet total of a difference from the start to end point. You want to make sure that you do not count the first line because that is where you're starting from, and then that'll make your values incorrect. So then now I'll show some different examples. You can see here some of these smaller circular items on, I think this is, I can't remember which island this is, but you see some of these smaller ones. Those are obviously kind of more mounds, more hills areas, and you can see these contour elevations closer to the water are a lot more gradual. They're not as bunched up, so it's a very gradual slope downwards towards the water. Moving on in contrast, so this is a little harder to see, but these contours are very close together on the right. This is Mount Rainier up in Washington. So you can see they're very close together, and then corresponding to a left of like a 3D rendering, you can see these tan lines in the middle. That is kind of the bottom of a kind of roadway or river with the mountains rising up on either side of you to show. And you can see the shallower contour intervals of this river in comparison to the steeper ones of the mountains on either side of said river. So then continuing on, we have another example of a ridge. Here it starts out flat and then more near the top, it's a little bit more steep, and then it slowly, gradually expands out with more spacing between the um, various contour intervals once you get towards the bottom of the slope. And then this is just one more. This can show you how complex 3D models can be. It can show you various things from ridges to kind of more flatter areas. It's just a way to show you overall topography, whether it's in a 2D versus a 3D, and how to correlate the two. And then this is just another one as well, more examples. Not much to see on this one. So kind of moving forward from there, I'll talk about slope and kind of slope ratios thing. So a slope ratio expresses the steepness of the grade as a percentage of the ratio. So for example, a 4-to-1 slope means for every 4 feet horizontally, you get 1 foot vertically. So that is a 4-to-1 slope. And for example, a 4-to-1 slope is the preferred slope for the final cover of a landfill. Per state regulations, we do allow up to a 3-to-1 slope in some instances, but generally speaking, a 4-to-1 slope is preferred. So then moving on, percent slope. What that is, it is the percentage of the vertical change to the horizontal change. So for instance, this is just another example of a 4-to-1 slope, but we did 100 feet by 25 feet to kind of make it a little bit more easier to understand with the percentage. So the vertical change was 25 feet versus the horizontal change of 100 feet. So with that, you do the 25 feet over the 100 feet times the 100 for changing it into a percentage, and you get the 25% slope, which corresponds to the 4-to-1 slope. Then moving on to slope conversion. So as I've been saying, 4-to-1, how you can do this is we have our 25% slope that we calculated previously. Now you can do the total horizontal distance divided by the percentage. So you traveled 100 feet horizontally divided by the 25%, that gives you the 4 or the 4-to-1. So that's how it's all connected. And then so now I will be going through a quick kind of exercise to show you just how to do it if you were to read a map yourself. So we are going to determine the slope between point A down here and point B up here as a percent and as a ratio. And so what we're going to first note is up here, point B seems to be between the intervals of 900 feet and 895 feet. And then down here, point A seems to be on 880 feet. And then another thing to note, we always look at the scale. Scale is how you can tell what it is. Not every map has the same scale, so it is important to know what scale you're working in to make sure that you're not getting incorrect numbers. So moving on to the answers. So we put point B at about 897 feet because it falls between the 900 and the 895. If someone were to tell me, oh, I think that's 896, more power, more power to you. I can't call you out on it, but I would say that's about roughly 897. And then for sure, point A hits on 880. So the vertical change that I see is 17 feet. So whenever this is measured with a regular ruler between point A and point B, that was 3.25 inches. And since we have 100 feet per inch, that gives us a horizontal change of 325 feet. Then to calculate the percentage, we're going to do the vertical change of 17 feet over the horizontal change of 325 feet times 100 to get it into a percent to get 5.23%. And then, of course, if we want to get this into the ratio, then we would do the 100 foot, or yeah, 100 divided by the 5.23 percentage that we previously calculated to get a 19.1. So for from point A to point B, roughly, for every 19.1 feet we go horizontally, we go 1 foot vertically. So then that is just a quick example. And just going to get a little bit more into general math of that you may use for a landfill. We mostly use this for areas of waste that we're placing and volumes of waste that sites may be taking. So the first one here is the area of a rectangle, obviously length times width. And then in this example below, the length is 980 feet by the width of 150 feet. It would be nice if everything was rectangular and simple like this, but it's not always. So then we can move on to, oh, the slides are out of order a little bit for me, but that's fine. So a way that we can use this as well is acreage. So 1 acre equals 43,560 square feet. I can never remember that myself. I always Google it, but so then the 147,000 square feet that we got from the previous example of this area of a rectangle, we can tell that this rectangle shows 3.37 acres. And then moving on to the area of a trapezoid. The reason we care about a trapezoid is generally most landfills also have an internal slope on either side. So this L2 represents the bottom of the landfill, and this L1 could represent the top of a landfill per se. So this whole shaded blue area would represent the area of fill that we have for a landfill. So then this is the area equation for a trapezoid. And then from this example, we have the 35 feet for the top plus the 20 feet for the bottom. We multiply that by 1/2 from the equation itself, and then we multiply it by the 10. So we get a total area of 275 square feet for this. Now, these are very simple examples. It's a good starting point, and a lot of consultants and people who design landfills have a lot more in-depth modeling and various things that they can use to actually determine areas of landfills. But this is just something to kind of give you a rough idea or a good starting point to kind of wrap your head around some more complex items. And I believe that's all I have. I know that was pretty quick, but I'm going to ask if there are any questions because I can't see the chat. So, if David, if you could let me know if there are any questions.
There are no questions.
Beautiful. Well, hopefully I didn't put y'all to sleep with too much math, but I'll leave y'all with that today. If anything pops up, feel free to let David know, and I could help with any questions that may
Yeah,
pop up later.
I'll let you know.